what they talk about is that metadata is what they consider a form of weak supervision because it's not necessarily correlated to the target, but it also has a little bit of additional information that we can inject. So they try to use this metadata to guide how the self-supervised learning works. And what they do is that essentially they have this metadata. So it can either be continuous, such as the time of the day, or it could be discrete, such as like the location or the antibody. And what they do is that they assign each metadata a type being informative, which means it's beneficial. We want to have the embeddings align more towards that, and spurious factors over here, which means that we should try to suppress them. And the thing is that assigning this metadata is actually kind of just messing around. So they talk about it being based on prior domain knowledge and simply just testing over the variables and seeing how it works. So the approach of kind of choosing this metadata isn't exactly that rigorous. It's just depending on how prior works happen. And actually, there's an interesting study in the appendix that shows that just because the domain knowledge suggests that we should suppress a specific factor, actually could harm performance. So there's a little bit of interesting concept of exactly what we should be suppressing and what we should be trying to promote. And going over the main system, so this builds off directly on a slightly modified Dino v2 structure. So we have the original Dino loss where we try to align an augmented form of the image with from the student model to the exponential moving average of the model to a cleaner version, non-augmented image. And we have the eyeball where we try to mask parts of the image and try to reconstruct them. And instead of the classic collier regularization, which tries to prevent clustering, we have the SIGREG, which is trying to project it to like a Gaussian distribution. And then now we have this additional loss term, which is essentially for each of this metadata, we determine if it's beneficial or harmful, and we try to either suppress it or encourage it further. And they actually do leave out some additional information on how this loss is calculated, which only shows up in the appendix. So there's a lot of interesting information in the appendix. And we also note that they use a single value for the hyperparameter, so 0.03. And like we mentioned beforehand, they don't really explain why they picked that. And they simply just throw out that variable and just use that for everything. And that's it, common.
So is it the case that this is supposed to be a general purpose, like augmentation to self-supervised learning objectives, or does it have to use Dino?
I think that essentially the actual FINO paper is just this added term. So it's kind of applicable to any type of self-supervised learning. So like, let's say we have like contrastive learning, like SimCLR or something like that, then we could probably replace the first three terms with that. So as long as there's like a single output, like a CLS token, or a single embedding that is the output of the model, I think this is kind of more like a general framework to just aligning it together.
Yeah, they don't show that though, right? Everything in this paper is doing this loss objective approach with the 4 different losses.
I think in the appendix they do show for SIGLIP too.
Yeah, I think they talk about, let me see. They talk about SIGLIP too. So honestly, I don't know too much about how this works, but they do show that it kind of works across. The thing is they do use the Dino loss. I'm not sure if the SIGLIP is like a different way of training or if it's a different model. So I'm not too sure. If someone knows a little bit more about it, they could jump in.
I mean,
the clip with the sigmoid loss, that's what I remember.
Empirically on labless, we have FINO applied to JEPA and FINO applied to Dino, and it performed better than both, but like without FINO. So theoretically, it works.
but the JEPA still has the that's only replacing IBOT, right? It still has dyno loss.
Yeah.
Right, but I thought your question was, can any loss be used in combination? So you're asking specifically about dyno?
Like, let's say we have, master autoencoder, right? No dyno loss. But so far, we've only been assessing with some modifications to the standard dyno.
Yeah, I think it's just more like a general framework of applying it. So I think at least for, autoencoders, the way of applying might be a little bit different since there's not like a clean CLS token or like a single output. And this probably works best on the single output because the suppression and like the alignment to the metadata is all applied on the CLS token. So like the main output. And if there's like a way of adapting it to other models, there's definitely a likely approach. And I think I'd probably go a bit more into like how the actual system works so we can kind of understand that a bit better. So in the terms of the methods is they have two different types of metadata. They have discrete and continuous. So the first way they do is for the discrete metadata, we have, let's say, different types of values specifically. So if you're talking about cancer, there's different types of cancer types. And what they do is they use something called prototype-based contrastive objective, which is essentially an alternative to normal contrastive learning. And for each of these metadata, we start with a randomly initialized prototype. And what we do is we have it that every time we get a prediction on that same metadata. So let's say we have bladder cancer. Oh, SIGLIP is like an improvement on CLIP. Okay, that's pretty interesting. I guess we can probably look into that a bit further after this. And going back to the explanation, so we have this embedding that is specific for each of this metadata, and every time we pass over that same metadata, so if we have bladder cancer, every time we get another bladder cancer image, then what we do is we do the exponential moving average on that. So we get the prediction of the bladder cancer image from the teacher, and then we try to improve on this prototype each time by taking the EMA on that. So over time, it starts following a bit more of the average of all of the metadata types. So for bladder cancer, it starts to follow a bit more on the average of all the embeddings of bladder cancer images. And then what we do is that since we have all of these prototypes, which are approximately similar to the average of each class, then we can do a contrastive learning on each prototype. So over here, we take the dot product with regard to each of the prototypes, and it tries to align the similarity as much as possible to its own prototype. So it's trying to align it to the average of its own class. And as a result, it's able to have like a way that doesn't include explicit positive and negative labeling, because for a lot of contrastive learning, it has exact, if it's the same class or if it's in a different class, and tries to align to the same class in a different class, but it requires all of these positive and negative labeling. And this prototype system doesn't rely on that. So that is definitely a way to scale with metadata. And the data that they do test on has a lot of classes. It has up to thousands of classes. So if we try to do contrastive learning on it, it simply wouldn't work out because there's too many classes that having positive and negative labeling would probably not work out exactly. Now for continuous metadata, what they do is they use a predictor, so like an MLP, and they try to simply regress the model to that objective. So I would argue that this is kind of a bit more like a hard loss, because contrastive is like a soft loss that tries to push things away, but continuous is definitely a much more direct approach. And what they do is simply just mean squared error on this prediction, and that is the result. And the difference between suppressing and having informative is that for informative, they basically apply just this normal loss and continue with that. But for spurious, what they do is they actually do the reverse of the gradient. So now what they essentially do is we have the attached head. So like the metadata or the continuous metadata, the loss, we try to improve this output, but we also want to make it that the model itself is going opposite of it. So it's doing gradient ascent instead of gradient descent. So it gets further away from predicting better on these outputs. So such as in a spurious correlation, we want it to be less correlated. So it learns the opposite side of it. We can see in the diagram over here that for any spurious metadata, they use the gradient reversal, which tries to make it further away from this objective instead of closer. And over here, we have a diagram that shows kind of how there's the different prototypes and how we try to align them with each other and further away from different prototypes.
So if you have continuous metadata, it's literally just like a supervision on top.
Yeah.
But for classification, why don't they do like cross entropy? Why are they making this complicated?
That is actually an ablation study later. And let me see. They actually try doing replacing it with the MLP classifier, but it actually makes the performance worse. So I think the reason is because cross entropy is kind of like this is just my idea, but I think it's a bit more like a hard constraint rather than contrastive, which is a bit like smoother, which also makes me wonder for like continuous variables, if there's a different way of doing it that's not so direct mean squared error, if there's also like a way of doing prototypes, like some type of discrete prototype for continuous variables, that might also make it better. But that's just like my few ideas, and I'm not too sure exactly how that would be implemented.
So the conclusion was that a hard supervision is worse, but for continuous, they're unable to think of a way to do it.
Actually, that was kind of my own. That was my own kind of explanation. I'm not sure if it's too supported because over here they just say it does better, so it's just a stronger benefit.
Well, if that's true, the metadata that's working for us is largely continuous. Maybe we can try breaking it up into categories.
Yeah, that would be interesting to see. Okay.
So when you say continuous metadata, what do you mean by that? What kind of data we're dealing with?
Oh yeah, so let's see if they have a good example. So actually I think they had examples over down here. Yeah, so over here we have discrete is like antibody and continuous is like the timestamp. So the time can vary over the day, but a specific like antibody is a discrete, like it can either have this antibody or a different one. A continuous is it can just vary over the time. Over here we have like the hour, the latitude, and the longitude. So it's not like specific discrete. It could only be like these 10 values. It can vary. So that's what the continuous and the discrete are, a little bit different. Yeah, over here, patient age, that is definitely continuous. But the way that we view an X-ray, maybe there's like 3 set ways we do an X-ray. And that is discrete because there's only 3 ways of doing it. And it's not like a smooth approach. Yeah, does that kind of clarify?
Yeah. Another thing, they mentioned they use informative metadata and spurious metadata. So it's like not all data is useful for us. Like first of all, how do they decide which metadata is informative, which is spurious, and if they're not sure if it's gonna if they know it's gonna hurt the performance and they have to deprioritize it, then why include it in the first place?
Yeah, so the thing is that the way that they assign informative and spurious is kind of just test around and see. So it's
domain knowledge, really.
It's just prior domain knowledge, just how it's deployed and just like trying to test it essentially. So there's not really a standard way of doing it. And the reason why they include spurious and helpful ones is that for spurious correlations, you kind of want to suppress it. So let's say, with the example I said beforehand, if the image is trying to learn like the time of the day specifically, and you don't want it to learn if it's daytime or nighttime, you just want it to like count the amount of cows there are, for example. then you don't want it to learn the timestamp. So you can try to suppress timestamps so it doesn't focus on the time of the day. Instead, it tries to focus on the other information. So that's where the spurious correlations come in. And for the beneficial correlations is, let's say, I'm not exactly sure what, let's say antibody. So if we want it to be related to a specific type of antibody, then we want to have it more correlated to that so that it learns a bit better from the biological aspect. Since antibody is directly correlated to the cells that we see. So learning antibodies in a better way would make the model learn the biology a bit stronger. So does that kind of answer?
So if they already know through domain knowledge and everything that these particular metadata are spurious, then why include it in the first place?
Yeah, well, the thing is that when we do self-supervised learning is we don't actually include any of this metadata. So through pure self-supervised learning, we get only these images. So let's say we have images of the daytime and the images of the nighttime, then it's going to start learning the difference between daytime and nighttime, but that's not exactly what we want. So the entire point of FINO is we try to add this metadata. So we want to either encourage useful stuff and suppress not useful things. And that kind of comes in with domain knowledge. So that is kind of what the objective of FINO is.
Oh, so you're actually not including timestamps.
Yeah.
It's like a learned behavior and you're trying to suppress that learned behavior.
Yeah, let's see, like over here, like the spurious metadata, we're trying to just guide it away from it. So we're trying to suppress that. But informative, we're trying to align a bit more.
I guess just to reword it to make it clear, like the baseline here is just like completely no label, no metadata, dyno self-supervision training. And the worry is that maybe it's finding some local minima of like predicting based on the time of day, based on the brightness of the pixels, or where the sun is or something. And maybe it does an okay job of that, but you don't actually want the model to do better if the input is daytime versus nighttime or something. So I guess if you're intentionally making the loss not learn that information, you get a more general purpose, generalizably useful model.
Yeah, that was a pretty good explanation of it. So,
well, I guess if you look at the UMAP for that, I think that HAP data, right? So they don't even include the one which suppresses the representations, right? If you see, I think they've explained there that they only use the antibody as the informative metadata, and that automatically kind of doesn't include the cell line, which is supposed to be a suppressor one. So yeah, I don't know if even adding one that suppresses even helps, because just adding the informative one kind of ignores the suppressor one. So not.
Yeah, I think one of the tests, I don't remember exactly which one it is, but they do suppress one of the variables and they also encourage a different variable. So they don't really go in depth to a lot of like their, honestly, like the explanations or different ablations. So I think it was FMAO or one of the objectives. They do suppress a variable and they also try to encourage a variable, and we can only see like the final result when they come together. So it's not like we can see exactly how one variable contributes and one variable does worse. So it's kind of limited in that kind of study. Yeah, so going back to this loss. So now that we understand how the prototypes work and the continuous, and we see that it's kind of just added on, there's a few other factors that's kind of missing from this loss function.
One more clarification question. So the continuous, when it is continuous metadata, there's no contrastive part at all? There's no track, because you get this assumed benefit of the discrete having like the contrastive pushing and pulling, and that's just not present at all if it's continuous.
It's just like an MLP to a regression loss. So that's probably like not the best approach. Maybe someone would like
surprising that they have this whole thing with the prototypes and everything, and just not applicable at all if it's continuous.
Yeah, so that would be like an interesting future direction to look at if you can do prototypes with continuous data or some other type that's not so like a hard loss, more like the contrastive, which is like softer loss.
The thing is, though, I'll just say a comment on this. There really isn't very much difference between this so-called contrastive loss equation 1 and the normal cross-entropy loss. Like the only effective difference is the temperature. You guys can correct me, but I think the only effective difference is the temperature and like basically the update rule for what the weights of the final, class linear layer are. Like if you just instead let these P prototype be just free parameters, they would be completely equivalent to a normal cross-entropy classification loss on top. I don't know if that made much sense, but basically there's very little difference between this and just doing a standard supervised cross-entropy loss, trying to predict the metadata category.
I mean, I think it is kind of interesting though that the results show that the MLP has like 3.8 decrease in performance. And okay, I guess my understanding of the cross-entropy loss might be like a little bit wavy because I haven't looked at the equation too much in depth. But I know that for cross-entropy, it's like we're trying to align it specifically to a different class. And that's like based on just the outcome. Over here, we're trying to like align it with each other instead of like a specific discrete output. So this explanation might be kind of bad. So you can just tell me if it's not the best. So we're trying to like align them with each other instead of to like an external class, I think. So that kind of might make it like a softer approach since we're just trying to pull things together and apart instead of like more separate.
If you go back to equation 1,
yeah,
you have the feature embeddings dot product with the prototypes. If you just think of these dot products, these are exactly the logits that go into the normal cross-entropy loss. And you can think of the P sub n, whatever, as the weights of the linear layer that you use to compute the logits. And it's being computed by dot product in exactly the usual way. The only difference is just that rather than having a normal linear layer, you have this prototype update rule and the temperature. But otherwise, this is the cross-entropy loss.
I thought the distinction is that with with the prototypes, like you're intentionally trying to make this one cluster that it's assigned to as unique as possible from all the other clusters. And so if you add more clusters, then it's making this, it changes how it's being calculated. But then for regression, it's just figure out the best way to predict it. And adding more or reducing clusters doesn't have the same.
Yeah, so maybe this is something where I'm confused, but I thought that the number of prototypes in the discrete case is just the number of classes for the particular metadata type. Says discrete metadata type T taking values in 1 to m. So m is just the number of different classes for this metadata category. If you have day and night, then it would just be 2.
Yeah, but you also have it being like attractors or repulsors, right? Like, I think that is correct, though, that just the number of classes is the number of prototypes.
Yeah, it is. Yeah, it takes 1 and m for each of the metadata.
I mean, in a way, that is what they're doing, right? Like you just classify, is this that nuisance class that I don't want, and then you do the reversal, and it makes sense why it's like a just cross entropy loss there, right?
Yeah, I guess if it's essentially the same, the only distinction is using these prototypes. So maybe the prototypes, the fact it's like an exponential moving average allows it for a bit more. Yeah, it's able to at least have.
But any linear classifier is a set of prototype. So the only difference is like it's just a classifier with EMA.
Yeah, it's the update rule. The EMA update rule is different from the gradient descent update rule. And I think that's the main difference. But I'm happy for anybody to.
In the appendix, why do they say that there are like 65,000 prototypes?
Oh, I think that those prototypes are for the Dino and the iBot heads. So those are a little bit different because each of these losses has like their own different prototypes. So Dino has like 65,000, iBot has 65,000, and then the metadata has like its own approach based on the prototypes given by the metadata.
Okay.
Okay, so
So the idea is that if they all share the same encoder, the adjustments in the FINO head prototypes should affect how prototypes are clustering on the other heads.
well, this is applied just on the CLS output. Let me see the diagram. Yeah, it's output on just the CLS token. And since the self-supervised loss has like their own projection to their own prototypes, there's probably a little bit of like impact to it, but it's kind of like they have their own different projections. So essentially it's just the encoder itself getting modified, and that could influence the Dino and the iBot as a result. Okay, I'm not sure if I answered the question fully properly.
No, you did.
Oh, okay, that's good. Yeah, so I guess on this, we probably have to look a bit more carefully, but at least right now, our consensus is that the EMA is what makes it do better. So applying something like that to continuous would be interesting, although I'm not too sure exactly how we would do that right now. So going back to how I was saying that there's a little bit missing from this loss function over here, they talked a lot more about how the system works in the appendix. So first of all, they have a very, yeah, so what they do is that instead of starting initially with just the FINO being fully weighted, they actually use the gradient flowing over time. So it increases over time to a value of 1. And this allows it to not have like a major shock when it's being initialized initially. And then another large thing that they have, and honestly, I disagree with this a lot, is, I find this kind of interesting, is they use per branch gradient equalization. So what they do is they realize that if they have different amounts of branches, they want to have similar amount of weighting for each of them. So for each of the branches, we have like the output and like the loss. And then they try to do a geometric mean across all of them to make it a bit more smoother. And then they try to weigh it such that each of the branches have the exact same weight compared to this geometric mean. And then after that, they apply it to each of these metadata losses. So essentially, they try to normalize it together and make sure that each of the branches have similar outputs. And I think the issue is that the explanation for this is that the losses would be corrupted by very different raw gradient magnitudes, but they kind of contradict that immediately because below they say that there's only 12% of a difference in the gradient norm. And then after that, essentially they talk about how this is for when there's multiple branches of outputs. And another issue is that they only test with one metadata, except for this one time where they use 2 metadata. So they only balance between two different heads for the metadata, and it doesn't really go in depth to an ablation study on exactly how much this improves performance or not. And the explanation for why they do this is kind of bad, because they say that it's supposed to suppress any different sizes in raw gradients, but they also said it's only a 12% difference. So they kind of contradict themselves on this, and I find that kind of interesting. Another critique I have on this is that essentially by doing this geometric mean target, we also lose a bit of factor importance between each branch, which could be harmful, because let's say we have a specific metadata that has a bit more importance compared to the other, then we lose the gradient norm information about that along the way. And furthermore, they do an extremely in-depth analysis compared to other multitask gradient balancing, which is interesting because they use only 2 branches for only a single one of their tests. And they mentioned that it's because it's supposed to balance between contrastive and regression losses, since those could have different magnitudes, but they don't support anything on if there's like 2 branches on contrastive or 2 branches on regression, if those have similar gradients, because the only explanation is that contrastive and regression have different norms. And finally, by testing on these different metadata branches, like the weighting on these branches is like 0.03. So they don't consider how it might affect the other types of losses, since they're stacking the dyno loss, the IBOT loss, the sig-reg loss, and finally these gradients. So the fact that they're focusing on like just the raw grading magnitudes of just the metadata instead of how it comes together with all of the other losses is something I find kind of limiting. And I think if someone's able to do like a test on balancing between and maybe even the other losses, or have a further ablation study on this gradient equalization, that would be definitely a lot more interesting. So with that being said, that covers most of how the training is done. A system that they use, though, is they also do warm up all of the prototypes first before they do the further training. So they freeze the encoder and they do warm up on the patch embedings, the dyno IBOT, and the metadata. That allows it for the metadata to at least have like a reasonable exponential moving average. So it's not starting off just with random noise. And after that, they train normally. So now moving on to the results.
Can we touch on the branches a little more? So just for helping me understand, a branch is what? It's like the CLS token gets a branch for every metadata type? Yeah.
So let's say we have like 2 metadatas, then we have, one output for one loss for the metadata 1, another loss for metadata 2. So they focus on how they could try balancing the losses between those 2 metadata.
And then what were they saying about like not being able to train multiple branches at the same time?
Yeah, their argument is
the magnitude is different.
Yeah, the argument is that when there's many branches, the intent for the losses are corrupted by different raw gradients. But then they talk about how the gradients are only 12% off.
Well, what's their solution, though? If they think it is a problem, they
use a geometric mean across all of the branches. So taking the losses, they take the geometric mean, and then they try to, for each of the branch, they try to normalize it to that geometric mean. So they divide it by the exponential moving average of the gradient norm for each branch. So now it's approximately equal to 1. And then they multiply it by the geometric mean to get the relative scaling. But this loses the information on each individual branch having their own different gradients, because let's say branch 1 has like the predictions are completely off and that needs to get better. It gets normalized together, so it kind of loses the per branch information, which is why I kind of disagree with this approach. And the fact that it's only 12% apart, and that's kind of like the whole argument that it's going to be extremely different. And they don't really support that with any ablation studies. So I find that this thing is kind of unsupported. And doing a lot of tests on it would probably be a lot more supportive of whatever argument that they're having.
Okay.
Were they able to get the positive and spurious to work at the same time?
Yeah, I think they did it for one of the tests. I think this one they use spurious as ear and subregion as beneficial, but it doesn't go.
What happens if they average like a positive gradient and a negative gradient?
I don't think they talk about that much. So yeah, I think there's a lot of things that could go a bit more in depth along the way. They do talk about how, like, some later factors, it's good to have like some other suppression too. Like if you're suppressing something, it's good to have something to encourage, but they don't support that also. They just kind of say it. Let me see what it says. Yeah, it's saying that it's good to have informative and have the suppressing in the same run, but they don't really say exactly how that works or the performance improving from that. They say that the per branch gradient equalization, so using the geometric norm, that would balance the pressures between them. And that's kind of how they explain that. Yeah, so the actual ablation studies that they kind of try mainly reside on each individual metadata. So they can see when you encourage it and when you suppress it, how well the metric changes. So there's some variables that are always spurious. There's variables that are always informative. And there's some interesting results on cell line, which is considered always harmful if you encourage it or when you suppress it. And they talk about that a bit later, which I think is pretty interesting on how there's kind of metadata that's correlated with one another and that causes some unexpected results. There's also some metadata that's always beneficial regardless of if you suppress it or if you encourage it. And this might be because it could be similar to like an auxiliary task that could be useful for the model to learn on. So, but for most of the case, we see that metrics are pretty standard, spurious or informative, which is pretty straightforward. Now, in terms of the actual performances, what they do is, honestly, over here, they show that it does better than supervised fine-tuning and FINO, but they actually leave out a lot of comparisons with the original Dyno model, which we can kind of see later here. So the way that they compare it is they use specialized state-of-the-art results, and they use citations there. They use supervised training, so you have the full model, and you train it from, they can do from scratch or from fine-tuning, but this is training on all the parameters. So they use, I think, a VRTL, so it trains on all 306 million parameters on likely the CLS token. There's domain adaptation, which tries to align source and target information. And essentially, the last one is representation adaptation, which they use either 3 approaches. So frozen model, they try to do, they try to attach like a linear probe on the top. Dyno self-supervised learning. So this is essentially, they try to do further pre-training. So I think a good example is what we try to do in like the nanopath competition is we have the frozen model initially. So like we build off the Dyno V2 checkpoint. And then we try to do self-supervised learning a bit further on top of that with the domain relevant information, such as the histopathology slides. And a very interesting fact is that this actually beats almost every single supervised training and domain adaptation already by itself. So we see over here, we get just normal self-supervised learning has performance of 60, which beats all of these approaches, 50, which also beats all of them. And this is like a common pattern. In comparison, we have FINO, which does slightly better than Dino. So the fact that they didn't show Dino beforehand kind of shows that FINO is honestly just like an add-on, but a larger claim that could come from this paper might be that using self-supervised learning instead of supervised training could actually have better performance. And that is kind of attributing to...
These are all simple probes as the evaluation though, right? Or not?
For supervised training, I believe like they train really like they make the backbone trainable. So they use like the probe on top, but everything's trainable. And that actually has pretty bad performance. Frozen model is they just add a linear probe on top. Dino self-supervised learning, they do self-supervised learning on the data first, and then they add a probe. And then
but it's the explanation that they're overfitting when they're doing full fine-tuning, and so it's not generalizing to this test set.
Yeah, I think that's mainly the explanation. I don't think I looked too in depth to the explanation exactly, but you can kind of see over here that when we use supervised baseline, it kind of collapses. Like the embeddings kind of go exactly into specific strong clusters, which is kind of harmful for some KNN scores over here. And we have self-supervised learning, which is it likes to be like much broader, have its own variant within it. And we have FINO, which tries to lead it a bit more into the metadata like clusters. And we see over here for spurious factors that supervised baseline actually has the least spurious factors over here. And self-supervised learning has the most. So what FINO does is it improves based on this self-supervised adaptation to reduce the amount of spurious factor, and also tries to improve upon the target variable. So the KNN for target variable goes up. So I think FINO is kind of like an add-on to self-supervised adaptation, and it kind of builds on top of it, but it's not like the make or break, in my opinion. Since we can see beforehand that Dino, just plain self-supervised learning, has probably the biggest jump in performance, and FINO is just slightly on top, which also makes it interesting why they didn't put that on here, because over here in the main results section, they don't show the Dino V3, they only show the frozen model. And then later there's a comparison. They do ablation studies based on the amount of data there is. They show FINO self-supervised training, and I think this is domain adaptation, but they don't show just Dino itself.
And there's also the nuance that they added SIGREG.
Yeah,
right?
They have ablation study here. It says SIGREG does better than Coleo, but I guess that could also be depending on like the specific task, because they use HPA on most of these ablations.
Yeah, so just swapping out Coleo with SIGREG gives them a benefit, and then there's basically even a smaller benefit if you're only doing an ablation of whether adding the metadata guidance stuff is helping compared to the Dino approach if you take that part out. And then also for our pathology stuff, we don't even use Coleo, we use KDE, and I don't know how that might factor into all of this as well.
Mm-hmm. Yeah, I mean the interesting thing is that MLP does pretty terribly. Like, I think it does even worse than without discrete guiding. That's pretty interesting. So I think honestly something that could be taken away is that the Dino self-supervised learning is probably the largest contributor to performance, and FINO is just slightly boosting performance, and they kind of try to make FINO look really good by kind of hiding some of the Dino information. And However, it still is beneficial in overall since it does have slightly better performance in all the categories. So that is still useful, especially in terms of like KNN. We can see that it becomes a bit stronger in both suppressing spurious and increasing the KNNs. And it also kind of just says supervised fine-tuning is pretty bad unless you have, I mean, it does worse than FINO in all cases, so it might lead to a lot of like model collapse if it's too specific. So another argument is that maybe just the dyno losses kind of force the model to continue learning like the geometric patterns. But if it's just purely self-supervised, I mean, if it's purely supervised, then it tries to focus purely on a task and loses some of the geometric level information along the way that actually might make it have worse performance.
Yeah, I mean, it seems to suggest that they're basically saying you're overfitting. If you're doing supervised fine tuning, it collapses on the dimensionality reduction plots.
Yeah,
but they didn't happen to do anything at like LoRa or ways of not doing full fine tuning.
yes.
Because that's kind of the maybe alternative most people would think of for the problem of generalizing, not being able to generalize well, but they still want to do full fine tuning. They would just do some sort of not changing every single parameter.
Yeah. Mm-hmm. Yeah. So besides that, there's the large limitations and considerations because metadata is like a weak supervision, and it's also difficult to see if it's like beneficial to encode or like suppress information such as like gender, geographic origin. So there's also like kind of the ethical concerns that you could, if let's say want to train on gender improves performance, so you kind of encourage that, but that could lead to like some more biases. So there's kind of like a trade-off there. And I think it would have been interesting if they tested on these more like ethical considerations, but they only kind of include on the side. Now, I think there's a few more interesting things left, which is the fact that...
By the way, you don't need the metadata for after you've trained the model, do you?
No.
It's just to help guide the representations, and then you can just use it as is, right?
Yeah. So it's just like a per training thing. So they do some analysis on specific metadatas, which does go into a lot of interesting results. So the first major thing they find out is that plate factor, which is considered by domain knowledge to be spurious, is actually beneficial when encouraged and harmful when suppressed. So this goes against a lot of domain expertise. And the thing is that it's because it's correlated to a lot of other informative metadata. So knowing plate can lead to information on antibody and the cell line. So it's correlated to informative. And as a result, trying to suppress that harms performance, and trying to encourage that is directly weakly corresponding to improving antibody and cell line. So this shows that simply like encouraging or suppressing domain expertise could actually harm performance unless you look carefully at how the metadata is corresponding to one another. So they talk about here that plate is the coarsening of both informative axes. And it said that once you include antibody, then the benefit is largely reduced, which makes sense. But I don't think they actually say like how much it gets subsumed. So they kind of just put that claim there. Oops. And then when you try to suppress it, it tries to suppress informative signal, which is also harmful. And they say that there's no antibody anchor, which since trying to suppress plate suppresses antibody and cell line, it results in worse score. But they don't test exactly what happens if you encourage antibody and cell line and suppress plate, which I think is kind of a big hole. and would have been really interesting to see. Now, another thing is cell line. So I think this uses some domain information because I didn't really understand it. So if someone knows a bit more about this, that would be useful. But what I can tell here is that cell line is expected to be beneficial, but it's actually like it harms performance when encouraged and when suppressed. And I think it's saying that potentially it being binary is too strong, that there's like, perhaps it should be a bit more continuous. And because of that, it could harm performance. But if someone has a better explanation, that would also be better. Yeah, so essentially they have a practical guideline based on these surprising results. So they talk about how it's important to check the dependence structure first, so that we know that you're not suppressing or encouraging something that could be correlated to other factors. They try to prefer positive guidance. So they're seeing that suppression does lead to potentially harmful results. So I think that's my phone. Okay, so I think that Hassan mentioned that suppression could lead to like worse results. So this kind of ties into how they're saying that positive guidance is probably like the safer approach than trying to suppress things. And lastly, they say never suppress an entangled factor in isolation. And this kind of goes back to how they're talking about how you shouldn't suppress the plate because that could be corresponding to the antibody and the cell line. And they say that we should include informative when you're trying to suppress an entangled factor, but they don't support this in like they don't support this with any numbers, anything like that. So it's kind of unfortunate. And they don't do any ablation studies on this either. And all the tests kind of show on either individual metadata or just a combination of two for that single topic. So there's kind of a lot of limitations on like their claims, which could probably be supported a lot through testing further, but also leaves like a lot of things open for clarifying and validating things further. So I think that essentially covers a large aspect of this, but a few ideas I had is just general questions is, so now that we know that it works a lot from metadata, and this metadata could be corresponding to a lot of labels, the thing is that they say that we're only using metadata, but what would happen if we try to use actual labels to adapt it instead of the metadata itself?
There's not really that much of a difference between a label and a metadata, which they call a soft label, right?
Yeah.
So
Yeah, what is an actual label?
Yeah, I think the thing is that it could kind of be expanded beyond just metadata, and you could essentially put in any additional information if you want. And I mean, because
That's kind of what we're doing, right? We're
so.
using gene expression, which is no one would call it metadata. You would call it associated data, and that's something downstream tasks would predict.
Yeah. So it could also be interesting to see what would have happened if instead of using like supervised fine-tuning, you use some of those labels as just the pure labels instead of metadata suppression. You see how that could affect. And yeah, another thing is that made me wonder is how these prototypes kind of need passing over them to update. And there's some of the data that they use is extremely sparse. They have like, I think 60,000 data points or like 10,000, like a few thousand classes. So this will lead to updating the prototypes to be kind of slow. So I'm wondering if there's like perhaps like a better approach to having updating, because otherwise the EMA might be a bit outdated for each of the prototypes. But yeah, that's like essentially a few side ideas. I know we were talking a lot about if this prototype system is a bit different than just straight up using what's it called, like classification, or like how we could try to use continuous metadata and potentially using prototypes for that. So there's a lot of room to explore further. And I think that's basically a lot of what I had in mind to talk about the FINO paper. So if anybody else has any thoughts, feel free to share them.
I have a question for like pre-training experts in the room. So if you look at the regression, like if you have continuous metadata that are using hard regression, to me, that's just a straight supervision loss. They call it weakly supervised in this paper. Like typically, let's say in the LLM world, why is pre-training always done after, supervised fine-tuning, why is it done after pre-training? Where in this paper, they're kind of getting at, you can do the supervision alongside the pre-training. And then they also show hard results that if you do supervised fine-tuning after the pre-training, it does worse than doing the supervision during pre-training.
It's not. That's what mid-training is, where you start mixing in supervised fine-tuning and structured data in your pre-training data. So we're doing LLMs and pre-training is doing that too.
So this is a common technique.
Yeah, it started when the open source training started picking it up with OMA 3, since they showed it working with reproducible artifacts.
And I guess maybe outside, like even take the ideas like even stronger. I think before that, like an older T5 work showed that you can really do like supervised task pre-training. Like if you just take a lot of different supervised tasks, you can use that as your pre-training in addition to like completely unsupervised pre-training. I think the challenge people had with that was you need to be very careful on how you balance the supervised gradient and the self-supervised gradient. And that's really hard to do in practice, right? Because T5 had like a ton of tasks, then they still struggled a lot. But in practice, you have like 1 or 2 tasks that you're interested in, and balancing that with like a huge pre-training corpus, it's going to be very difficult in practice.
Well, I think that it kind of shows through most of the results that at least using, like keeping a lot of the self-supervised loss along with doing training does better, because we saw how just pure fine-tuning kind of collapses in performance. But even just using self-supervised learning straight up is able to have a lot of this recovery. So over here, yeah. So perhaps just adding like the supervised, bit of the supervised noise while maintaining the geometric aspect is probably like maybe a better approach than just straight up just trying to supervise it.
Yeah, I do think some like correct kind of balance between them would help both of them. I was more like responding to why Hassan was asking, why do you not just add this during pre-training? And I think it's harder to do that.
Yeah, I guess also based on the balancing losses, it could also be interesting to, they had a whole like 3-page section on, like 2.5-page section on how to balance between the branches. So maybe if there's like a way to balance between like the dyno loss, like the segreg, and the metadata loss, or I mean, if you want to use like actual labeling, you could try, and have like a balance between all of those losses could also be interesting, because I know you mentioned that it's difficult to balance between self-supervised and some of the actual labeling information. So testing around with that could also lead to potential better results than what they had over here.
Yeah.
Yeah, does anyone else have like any final thoughts or like reflections on this paper or anything that they found interesting with it?
I'm satisfied. I think we covered most of everything.
Yeah.
Had a pretty long discussion.
Okay, I guess if like, no one else really has much more to say, then that's probably most of the discussions wrapping up.
Yeah. Thanks so much, Ryan. You did a great job walking us through this. Thanks so much for volunteering to, lead this journal club. I think it was very useful for all of us. And excited to continue to see if we can extract some signal out of this FINO approach. Let's all thank Ryan. And thanks everyone for coming. I'll share the recording in the Discord. And hope everyone has a good rest of the day.
Thanks a lot.